Hi, it's Femi from Science Hub and Tech. Welcome back. Okay, so I want you to look at this. Here's an open set on the real line. It's messy. It's got pieces scattered all over the place. Some of those pieces are tiny, some are wide. Here's my question. Is there some kind of hidden order inside this mess? Can every open set on R1, no matter how complicated it looks, be broken down into simple, understandable pieces? The answer is yes. And the pieces? They're just open intervals, every single time. After the break, we'll jump right in. Don't go anywhere. Definition 3.9. Let S be an open subset of R1. An open interval I is called a component interval of S if I is contained in S, but no larger open interval containing I is still inside S. What does that mean? A component interval is, one piece of the set stretched out as far as it can possibly go while staying inside S. It's a maximal piece. You can't make it any bigger. It's like, imagine you have a hallway with some doors open. Each component interval is the longest continuous stretch of open doors you can walk through without hitting a closed one. Theorem 3.10. Every point of an open set S in R1 belongs to exactly one component interval. They don't overlap, they tile S perfectly. And then comes the showstopper. Theorem 3.11. Every non-empty open set in R1 can be expressed as the union of a countable collection of disjoint open intervals, namely its component intervals. This is remarkable. No matter how complicated an open set on the real line looks, maybe it has infinitely many pieces, maybe it's some bizarre-looking thing, it can always be broken down into countably many non-overlapping open intervals. That's the anatomy of openness in R1. At its core, every open set is just a bunch of open intervals sitting side by side. And this representation is unique. There's only one way to do it. One more beautiful consequence. An open interval cannot be expressed as the union of two non-empty, disjoint open sets. Apostol calls this property connectedness, and we'll define it properly in Chapter 4, Section 4.16. But the intuition is gorgeous right now. An open interval is one piece. You can't crack it into two separate open chunks. It holds together. Now, what about the opposite of open? What about sets that include their boundaries? That's the world of closed sets, and it's coming next. So we've spent all this time talking about open sets, sets where every point has room to breathe. But now I want you to think about the opposite situation. What if a set traps its own boundary? What if the edge is part of the set? What if there's no escaping to the outside? That gives us a completely different kind of set, and it has a very satisfying name. Definition 3.12. A set S in Rn is called closed if its complement, meaning Rn minus S, all the points that are not in S, is open. So a closed set is just a set whose outside is open. The stuff that's not in the set has breathing room. Let's check our favorite example. The closed interval AB. Is that really closed? Well, what's its complement? It's everything to the left of A and everything to the right of B. Negative infinity to A, union B to positive infinity. And that's a union of open intervals, which is open. So yes, the complement is open, which means AB is closed. The name fits. Now be very careful here. Open and closed are not opposites in the everyday sense. A set can be both open and closed, like the empty set or the entire space Rn. And a set can be neither open nor closed, like the half-open interval 0, 1 in R1. The endpoint 0 makes it not open, and the missing endpoint 1 makes its complement not open either. So it's stuck in between. It's like a door that's not fully open and not fully closed. It's just, ajar. Now here's a beautiful consequence, and watch how it mirrors the open set theorems. Theorem 3.13. The union of a finite collection of closed sets is closed, and the intersection of any collection of closed sets is closed. See how it's the mirror image? For open sets, unions are always safe, and intersections need to be finite. For closed sets, it flips. Intersections are always safe, and unions need to be finite. These are dual statements. They're like two sides of the same coin. And Theorem 3.14 gives us a nice bonus. If A is open and B is closed, then A minus B is open, and B minus A is closed. Open minus closed stays open. Closed minus open stays closed. But here's a question we haven't answered yet. What about points that aren't in a set but are somehow touching it? Stuck to it? That distinction between being inside, being outside, and being on the boundary, that's where we go next. Thanks for watching.